See, today we are going to discuss about the topic graphs. So first let me say what is meant by graph. So graph is nothing but collection of vertices and edges. So graph is similar to that of tree. The main difference is graph is a cyclic tree. So you can also define graph as it is an ordered set of thing where we have vertices and edges. So you can represent graph as G of V comma E, where V is the vertices and E is the edges. Graph can be classified into two types. One is directed graph and another one is undirected graph. In undirected graph, we don't have directions in the edges. That means, see this diagram? See here, this is a graph where we have 5 vertices A, B, C, D and E, and the link that is between these two vertices, between A and B, we are having a line. It is nothing but an edge. So in this edge there is no direction. So therefore this graph is called undirected graph. Next one is directed graph. In directed graph we have directions associated with edge. See here, in this edge we have directions, A pointing to B, right? So therefore this is a directed graph. Now let's see some of the terminologies associated with graph. We have some terms like path, closed path, symbol path, connected graph, cycle, etc. So let's see one by one. So path is nothing but the way on which we traverse in a graph. In this we have closed path. What is closed path? In a graph we have vertices, no? Another name for vertices is nodes. If the initial node is same as the terminal node, then the path is called as closed path. If in this closed path, if the path is symbol, that means if all the nodes of a graph are distant, then it is called as a symbol path. Next one is cycle. A cycle can be defined as a path which has no repeated edges. Next one is connected graph. Connected graph is one in which there exists path between every vertices. Between every two vertices, we have some connections. There is some path is there. Such type of graph is called connected graph. Next is complete graph. Complete graph is one in which every node in a graph is connected with all the other nodes. And a complete graph will contain n into n minus 1 by 2 edges, where n is nothing but the number of vertices in a graph. Vertices, you can also call it as nodes. Next is weighted graph. Weighted graph is nothing but a graph on which some positive value will be indicated above the edge. That positive value is the cost for traversing from one node to another node. So such graph is called weighted graph. Next is digraph. Digraph is nothing but the directed graph in which each edge of a graph is associated with the directions with the another node. Next term is loop. An edge that is associated with the similar endpoints. If it starts from one node and ends with another node, the link or the edge that is associated between those 2 points or 2 nodes is called a loop. Next term is the adjacent nodes. Adjacent nodes are also called as the neighbor nodes. That means the node which is near to the already existing node is called as adjacent node. Next term is degree of the node. Degree of a node is nothing but the number of edges that are connected with that node. So if 5 nodes are connected, so 5 edges are connected for a particular node, then the degree we used to call it as 5. If there is no edge, only one node is there, then it is called as isolated node because the degree is 0. Now we will see the representation of graph. First one is sequential representation. So in sequential representation, we use adjacency matrix to store the mapping. See here, this graph is an undirected graph because there is no directions. We are going to map this in an adjacency matrix. So we know that in matrix we used to represent by row column, right? So here its dimension is represented as n cross n. See here the nodes A, B, C, D and E. These are the nodes. So that will be represented here A, B, C, D, E. And here also A, B, C, D, E. Like that we have to write. Okay, rows column wise. And see here from A we can traverse to B and we can also traverse to D. And whether there is any link between A to A? No. So from here, from A to A, there is no link or no edge. So we have to represent it as 0. Then from A to B, there is a link, right? So from A, you can move to B. So therefore, from A to B, the value is 1. If there is a link between a node, then you have to put 1. Otherwise, 0. See, from A to C, is there any direct link? No. So from A to C, the value is 0. The next one is A to D. This is A node and this is D node. From A to D, we have a edge. So therefore, have to put the value 1. Next, A to E. This is A node, this is E node. From A, there is no direct link between A and E. Right. So therefore, we have to mark it as 0. This should be repeated for all the nodes. See for the next one, from B to A, this is B node and this is A node. From B, you can traverse to A node because it is an undirected graph. So B to A, the value is 1. What about B to B? The value is 0 because there is no link between B to B. So this is an example for adjacency matrix drawn from an undirected graph. Next, let's see the adjacency matrix for a directed graph. See here, this is an example for directed graph. So we are representing it in this adjacency matrix form where, as usual, see from A to A, there is no link, so 0. From A to B, we have a link, so we are representing it as 1. From A to C, no link, so 0. From A to D, we don't have link, so we are representing it as 0. Why? From D to A, we have link, but from A to D, we don't have link. Okay, because it is a directed graph. Next one is the weighted directed graph. From weighted directed graph, you are going to write the adjacency matrix. What is weight of a directed graph? The positive value that is placed above the edge. This is nothing but the edge. The value which is placed above the edge is called the weight. So here from A to B, is there any path? Yes. And what is the weight? 4. Here you should not put as 1. Instead, we have to place the weights. Then from A to C, there is no direct link. So we are placing it as 0. Then B to A, we have a link from A to B. But we don't have a link from B to A. See, because it is a directed graph. So from B to A, there is no link. So we are marking it as 0. From B to A, 0. From B to B, also there is no link. There is no self loop here. So it is 0. Then what about B to C? From B to C, we have a link. And what is the weight? 2. So we have to mark it as 2. Likewise, you have to proceed. Next representation is called as linked representation. So in linked representation, from the graph, you have to represent in the form of like linked list, where we used to place the value and also the next box will hold the address. So here, this is an undirected graph and we are representing it in the form of a linked list. So from A, you can move to B. So from A, you can traverse to B. And from A, you can traverse to D. So it means that from A node, we can traverse to B node and to D node. After that, There is no any other nodes connected to A. So we are marking it as null. We are putting cross here. No, it indicates that no further nodes connected to A. Clear? Next, consider B node. From B, you can traverse to D, you can traverse to A node, and you can also move to C node. So from B node, you can move to A, D, and C. Only 3 nodes. So after that, there is no further nodes connected with B. So therefore, we are marking it as null. We are putting cross means no further node. This represents end of the node. Clear? Next, similar to that, next, consider C node. From C, you can traverse to B, you can traverse to E. So from C, you can traverse to B and you can traverse to E. Only 2 nodes. So we are marking it as end. So likewise, you have to proceed for all the nodes in a undirected graph. So this representation is called as linked representation of a graph. Clear? Yes. Now we will move to the next one. This is also the representation of a linked list, but here we are coming with directed graph. In the previous slide, we have seen undirected graph. No, so this one is directed graph. So from A, we have a node B alone. So from A, B. And the next end. No further nodes connected with A node. Then what about B node? So from B, you can move to C as well as to D. So from B, you can move to C node, you can traverse to D node. No further nodes. So therefore, you have to represent end of the node here. Then what about for C node? Only E alone. There is connection only to E node alone from C. So therefore, from C, E. Then what about for D? A. From D, you can traverse to A. Then from E, you can traverse to D node. Understood? Now, in a directed graph, the sum of length of all the adjacency list, this is the adjacency list, the sum of length of all adjacency list is equal to the number of edges present in the graph, right? One is weighted directed graph. So for weighted directed graph, you're going to write the adjacency list. This is similar to that of writing the adjacency list for a directed graph, but you have one more field which is nothing but a weight field. So it means that, see here, from A, you can traverse to B. So from A, you can traverse to B and you need to put one extra field here for placing the weight. What is the weight or what is the cost for traversing from A node to B node? It is 5. So you have to represent here. And from A node, there is no further nodes connected. So you have to mark it as end. What about for B node? From B, you can traverse to C node and also you can traverse to D node. So from B, you can traverse to C node and for C, the weight is 2. Right? And you can also traverse to D node and the weight is 8. Similarly for C node, you can traverse only to E node and the weight is 4. Weight is the value which is represented above the edge. Okay. Likewise, you can write the adjacency list for a weighted directed graph. Next one is breadth first search algorithm. Okay. So there are 2 main algorithms connected with this graph. One is breadth first search and the next one is depth first search. Okay. So this breadth first search is applied or it is used in many places. So wherever you want to find the neighboring node or neighboring network or neighboring location, we can make use of this breadth first search algorithm. So it can be used as a traversal method to find out the neighboring nodes in a network. And similarly, it can be used in web crawlers to create web page indexes. And also it can be used to find out the shortest path and also to find the minimum spanning tree. Now this is a graph. It is a directed graph, and the adjacency list is also represented here. See, for A node, the adjacency node is, that is the adjacent node is B node and D node. So for A, B and D. For B, it is C and also F. For C, the adjacent nodes are E and G. What about for G? It is E node. For E, the adjacency nodes are B node and also F node. And for F, you have only one node, that is A. And what about for D node? The adjacent node is F. Likewise, we can represent adjacency list. And now you are going to find out the traversing path using breadth first algorithm. So in breadth first algorithm, you have to traverse in a breadth-wise manner, not in depth-wise. So for A node, from assume the source node is A. So this is A node. From A, you can traverse to B and D. Is it not? So from A, you can traverse to B. After that, you should not go to C node. You have to move to the neighboring node of A node. So from A, B and then D. After that, from D node, what is the neighboring node we have? From D node, we have F node. And also from B node, we have the neighboring node as F. So the path is A, starting node A, B, D, F. Yes. Then what is the neighboring node for B and F? B has neighboring node as A. Already A is visited. Already B is also visited. So from B, you can traverse to C node. So after F, you have to traverse to C node. From C, you can traverse to E node and also to G node. So from C, have to traverse to G node and then to E node. Likewise, you can traverse using BFS algorithm. So the path for traversing using breadth first algorithm according to this graph is A, B, D, E, C, G and next is the complexity of breadth first search algorithm. So the time complexity for breadth first algorithm is O of V plus E, and the space complexity is expressed as O of V. Next is the depth first search algorithm. So here, instead of moving in a breadth-wise manner, we have to move in a deeper way. We have to move deeply. So that is called as depth first search. Depth-wise, you have to move until we find a goal node or until we reach the leaf node, that node which has no further children. And afterwards, we again backtrack from the dead end towards the most recent node that is not yet visited. So this is a concept of depth first search algorithm. Now we will move to an example. See here, this is a directed graph. Assume H is the source node. So now we will traverse using depth first algorithm. So from A, from H, we have to move to A because the neighboring node of A is H is A node. So from H, we can traverse to A. And we should not move again to the next side because it is depth first search algorithm. So you have to move deeper till we reach a node that has no children. So from H, we have to traverse to A node. From A, you have to traverse to D. From D, F. Then from F, we don't have any other way to move to the right side. it's enough for us to move to A. Already A is visited. So next one is B. So from F, you have to traverse to A node. From A node, you have to traverse to B. From B node, you have to traverse to C. From C, you need to traverse to G. From G, you can move either to H or to E. Already H is visited, right? It is a source node. We traverse from there itself. So from G, you have to move to E. So the sequence for traversing according to this directed graph will be like this. H, A, D, F, then B, C, G, E. Clear? Next one is spanning tree. What is spanning tree? So spanning tree is nothing but the subgraph of an undirected connected graph. So you can create many subgraph from a main graph. Such type of subgraphs are called as spanning trees. So spanning tree is a subset of graph that does not have cycles. The spanning tree should not have cycles and it has n-1 edges. The number of edges is n-1. And now let's see the applications of spanning tree. It is mainly used in computer networks, in routing cases, in routing protocols it is used, and also in cluster analysis. This concept, the spanning tree concept, is mainly used in cluster analysis and data mining, and also in routing protocol in computer networks. Now this is an example for spanning tree. So actually it is a spanning tree. From this spanning tree we are going to draw, this is an undirected graph. From this graph we are going to draw spanning tree. See here, the nodes are represented like 1, 2, 3, 4, 5. You can replace it by A, B, C, D, E. Like that you can replace. Okay. And this is an undirected graph. And from this undirected graph, you are going to draw spanning tree. So spanning tree is nothing but what? A subgraph. Okay, which does not form cycles. So you can draw a graph like this. From 1, 2, 3, 4, 5. This is one way. But we should not join again this to 1. Similarly, you can start and you can move in the right side direction also. I will show this here. See that 1, 2, 3, 4, that numbers are replaced by A, B, C here for our convenience. So these are the different spanning tree drawn from the previous undirected graph. See, all the nodes should be there. What are all the nodes we are having in a graph should be there in a spanning tree, but it should not form cycles. It should not form any cycles. So A, B, D, E and C. Next is spanning tree A, C, E, D, B. Another spanning tree can start from B, B, A, C, E, D. Likewise, you can draw many subgraphs. And now we will see what is minimum spanning tree. On these spanning trees, we have weight. See this graph? This is called as a weighted graph. Weighted graph is nothing but the weight or the value which is assigned on an edge. So when you have this weight, based on this weight, we will construct spanning tree, and which spanning tree has a less weight or less cost will be considered as minimum spanning tree. So minimum spanning tree is defined as a spanning tree in which the sum of weights of the edge is minimum. So this is a graph. From this graph, first we are going to draw, it's a weighted graph. From this weighted graph, we are going to draw spanning tree first. From this spanning tree, we can find the minimum spanning tree. So 4 different spanning trees are drawn from the previous weighted graph. See, B, A, C, D, and the weights are also placed over it. Similarly, A, C, D, B. The weights are placed here and the weights are also calculated. See, what is the sum of weights of this spanning tree? It is 14, right? 5 plus 6 plus 3, 14. Similarly, here the sum is 11 for the second spanning tree. For the third spanning tree, the sum of weight is 13. For the fourth spanning tree, the sum is 10. From among these four spanning tree, the last spanning tree has less weight because the sum is only 10. So this is called as the minimum spanning tree. All the four graphs are spanning tree, but the last one is the minimum spanning tree as it has less weight because the sum of weight is less when compared to the other three spanning trees. Clear? So the minimum, the tree, spanning tree which has the minimum weight will be considered as the minimum spanning tree. To find the minimum spanning tree and to traverse it, we have two main algorithms. One is Prim's algorithm and another one is Kruskal's algorithm. So these are the two greedy algorithms which is mainly used for finding minimum spanning tree for a connected weighted graph. One is Prim's algorithm and another one is Kruskal's algorithm. Now we will see some of the gate questions. See here, this is a directed graph given which has around 6 nodes. You can also call it as vertices. See A, B, C, D, E, F. So this is a directed graph. The question is the number of different topological orderings of the vertices of a graph is dash. You need to find the number of different topological ordering of vertices. Topological ordering is nothing but a linear ordering of vertices. Linear ordering. One by one we have to move. So that is nothing but linear ordering. So how many number of different topological orderings are there in this graph? 6. So the answer for this question is 6. Clear? Next question. Consider a tree arcs of a breadth first search traversal from a source node W in an unweighted, connected, undirected graph. The tree T formed by the tree arcs is a data structure for computing. The 4 options are given. The shortest path between every pair of vertices, the shortest path from W to every vertex in a graph, the shortest path from W to only those nodes that are leaves of T, and the longest path in a graph. So the use of breadth first traversal from the source node. Here the source node is nothing but W. Here it is to find the shortest path from the source node W to every vertex in a graph. So the answer for this question is second option B. The shortest path from W to every vertex in a graph. Next question. Let G be a graph with n vertices and m edges. So G is nothing but a graph with n vertices and m edges. What's the tightest upper bound on the running time of depth first search on G when G is represented as an adjacency matrix? So when you represent a graph in the form of adjacency matrix having rows and columns, you have to find the tightest upper bound on the running time of breadth first search on the graph G. The tightest upper bound on the running time of depth first search on a graph is an order of n square, where n is the number of vertices. So the option C is the correct answer, order of n square. Next question. In a depth first traversal of a graph G with n vertices, k edges are marked as tree edges. The number of connected components in G is, options given, A, option A is K, option B is K plus 1, C is N minus K minus 1, and next option N minus K. The question is, I repeat again, in a depth first traversal of a graph G, the number of, here the vertices are represented as N and edges as K, and the number of connected components. So we need to find the number of connected components in a G. How to find the number of connected components? It is edges is K and vertices is N. So how you have to find N minus K, vertices minus edges. So the option is D. D is the correct option. Next question. Consider this graph. This is an undirected graph. We need to find the depth first traversal of the above graph. See here, what are the depth first traversal of the above graph? 4 options are given like A, B, E, G, H, F, A, B, F, E, H, G, A, B, F, H, G, E, A, F, G, H, B, E. So what are the depth first traversal for this graph? See here, from A, you can traverse to B, this one, A. So the traversal is A, B, E, G, H, F. This is one depth first traversal. What is another depth first traversal? From A, we can move to B, from B to F, then H, G, and E. This is the second depth first traversal. What is the next one? Any other traversal is there? S. What is the next one? From A, you can traverse to F, then to G, H, B, and E. Right? Among these 4 options which are given, so we found 3 traversals. What are the traversals? The first one, third one, and fourth one. So option D is the correct answer. The question is given here. What are the depth first traversal of the above graph? 1, 2, and 4 only, 1 and 4 only, 2, 3, and 4 only, 1, 3, and 4 only. So the depth first traversal for this graph is 1, 3, and 4 only. Okay. So I hope you enjoyed this class. Thank you all.